Class. Today we are working on the very first lab. This is actually the first part of the first lab. There'll be two videos. The first video here I'll talk about the assignment that's on Blackboard, and the second video we'll talk about the assignment that's in the actual lab book. All right. So there's two things you want to make sure that you have access to is the assignment and the conversion chart. If you go on Blackboard, you can download and access both of those. Here is our Blackboard course. We've got the upload place here, so when we're all done, we'll upload our file here. We've got the lab part that I'm working on right now, and then this conversion chart too that will help us with this first part. Okay, so working on the first part here, we're going to complete the following conversions for the first part here. So we want to take 10 miles, and we want to put this into kilometers. And so we don't know how many kilometers that is. That's what we're trying to figure out, okay? We can use our conversion chart. So I like this conversion chart personally because a lot of times when you do conversions, you're multiplying or you're dividing, and it often gets kind of confusing for a lot of students. But with this conversion chart, you're only going to multiply, which is really nice. You're only going to multiply when you use this conversion chart here. And so it kind of simplifies it, I think, a little bit. So grab your calculator, grab your phone, or grab whatever, all right? And let's do the first one together. So 10 miles equals how many kilometers? So we're going to look at our conversion chart. Down here it says miles, all right? And we want to go from miles, go across to kilometers here. And so we're going to multiply by 1.609, okay? So I'm going to take 10 miles. I'm going to put it into my calculator, 10 times 1.609, all right? Then I am going to hit enter, and the answer is going to be 16.09 kilometers, all right? 16.09 kilometers. I'll show my work over here. All I did was 10 times 1.609, all right? And that equals, right, 16.09. And our new unit's going to be kilometers, right? So make sure that you always include your units. For these up here, your units are already kind of built in, okay? I'll do one more with you guys. So 1 foot equals how many meters, all right? 1 foot, all right? So we go over here on the left, we find feet, all right? So feet's right here. We want to convert feet to meters, all right? What we're going to do then is we're going to multiply it by 0.3048, all right? Let's show our work. So 1 times 0.3048, what's that going to equal? Well, 1 times anything, right, is always whatever it is, right? So the number is actually not going to change, right? It's going to be 0.3048 meters, right? So that's what I'm going to put in my answer here, 0.3048, all right? And again, we already have the units, so we're good, all right? So keep doing this then for the rest of this part. If you got questions, again, always let me know. Happy to help, okay? Down here, use a ruler to help you draw a line segment that has exactly a length of 1 centimeter. If you printed out the lab, this is actually pretty easy, or there are various tools you can use in Microsoft Word or various other software tools, all right, that you can use to draw a line 1 centimeter long. There should be at the back of the lab book rulers that you can use to draw a 1 centimeter line. You can even use like your phone. There are apps you can download that it can measure, and you can then use those to draw a 1 centimeter line with, okay? Down here for question 3, every material has mass, and that mass can be weighed, right? And then every material has a volume of space that it occupies. And so when we take our mass and we divide it by our volume, we get our density. So density is equal to mass divided by volume. Different materials have different densities, all right? Explain then how you could use a small graduated cylinder and a gram balance to determine the density of water, okay? What is a graduated cylinder, do you know? Graduated cylinders are really smart cylinders, right? They've graduated from school. No, I'm kidding. Graduated cylinder. I'll show you guys a picture here, just in case you don't know. Haven't seen one before. Just doing a quick Google search here. Graduated cylinders are things like this, and so they are these tubes right here, and if you pour liquid into them, they'll show you how much of that liquid you have. They'll give you the volume. These are usually in milliliters, but they can be in other units, all right? So how would you use a graduated cylinder and a mass balance, a scale basically, to figure out the density of water? Well, you have to figure out two things, right? You have to figure out To figure out density, right, you need to know the mass, you need to know the volume, right? The volume's pretty easy, right? You would just pour the water into the graduated cylinder, right? And you would read off from the cylinder, and that would give you the volume of water. But how would you measure the mass of water? If you were to pour that water like onto a scale, it would just go everywhere, right? The water is a liquid, right? So how could you measure then the mass of water? That's a question I'm going to leave up to you. If you're really stuck on it, again, let me know. Happy to help. Okay. How would you measure the density of a rock? All right. Well, measuring the density of a rock would be pretty easy. Well, part of it would be pretty easy, right? The mass of the rock would be pretty easy to figure out. You take your rock and you would put it on the balance, right? And you would read off then. You'd read off how much, how heavy that rock is, how massive that rock is based on the number the balance would give you, right? Just like you would figure out your mass, right? You could stand in a scale and you could get your report of your mass. Usually we talk in the English units in pounds, right? How many pounds, how heavy are you, right? Same thing is true with rocks, okay? But then how would you measure the volume of a rock, right? You can't just take a rock and throw it in a graduated cylinder. Rocks aren't liquids, right? They are rock shaped, right? So how would you do that? So think about how you would measure the volume of a rock and how you would measure the mass of water. Kind of the two questions there for you in part 3, all right? Down here, we're measuring the width of this piece of paper, so another measuring question. We want to measure this in centimeters. CM stands for centimeters, and we want to convert our answer into inches. So we can use our conversion chart again to convert from centimeters into inches, okay? So that conversion would be here centimeters. We want to go into inches, and so we would multiply by 0.3937, okay? Down here for 3 and 4, we're calculating the area of the piece of paper. Remember, the formula for area is length times width. And then we're figuring out the volume of a cube. Our cube is 4.5 by 3 by 5.5 centimeters deep. And so the equation is length times width times height. Remember, too, for question 3 here, your answer is going to be in units squared, right? Whenever you measure length times width, whenever you get area, that's square. Probably square inches, so make sure that you include that as your unit. And then if you're doing volume, length times width times height, that's centimeters, right? That's our unit, but we're cubing them, right? So it's centimeters to the 3rd power for question 4. So don't forget your units. And then down here, we're working on a rate questions. So a rate is when we measure rate is equal to distance divided by time. I'm going to pull out my annotating tools here. Just going to kind of draw on the paper here, but rate, this is not my best handwriting, rate is equal to distance divided by time, all right? And so maybe you've never encountered rate, but I believe you probably have. If you've ever driven a car, if you've ever been in a car or been on a plane or something, we talk about rates all the time. We talk about like speed, right? Speed, like miles per hour. In Texas, right, the speed limit might be, I don't know, what's the speed limit in Texas? There is no speed limit in Texas, right? But on some of the roads near me when I drive to work, the speed limit is 40 miles per hour, right? So 40, right? 40 is our distance, 40 miles, right? This is really bad handwriting. I'm writing with my mouse. 40 miles, and our time would be hours, right? Down here, right? So 40 miles per hour, that is a rate. That's what rates are. Rate is equal to distance divided by time, all right? Yeah, so talk about that miles per hour is down here. Sometimes we'll say like kilometers per year, all right? Note that distances must have proper units, kilometers, for example, and time, all right? And therefore, rate must have proper units as well. So the first question here, we're talking about the movement of a glacier. So glaciers are big chunks of ice, and they slowly slide downhill. So glaciers don't typically move very fast. And so we're going to get something that's kind of slow, I'm guessing, for question 5, all right? Was mapped. The glacier was mapped in 1911. Then in 1983, the same glacier was measured and located 4.6 kilometers further up the valley than in 1911. So the glacier has melted. This is a big concern. We'll talk more about this as the semester goes. But the glacier has melted, and it's retreated up the valley 4.6 kilometers. All right, so the glacier's gotten smaller. So they want to know what is the rate that the glacier retreated up the valley during this time span. So in order to figure out the rate, we need to figure out the distance, and we need to figure out the time. Okay, so they actually give us the distance, which is nice. They give us the distance of 4.6. All right, so I'm going to put in 4.6 kilometers for our distance. Equals D. All right. Now we need to figure out the time. All right. And so the glacier was first measured in 1911, right? And then it was measured again in 1983. So we need to subtract 1911 minus 1983. So I'm just going to do 83 minus 11. That gets us 72 years. So 72 years is equal to our time, okay? And so our rate then is equal to distance divided by time. So I'm going to punch into my calculator. Clear that out. 4.6 divided by 72. And I'm going to get a small number, right? I'm going to get a pretty small number. I'm going to get 0.063. I'm going to round it 9. And this is kilometers divided by years, okay? 0.639 kilometers per year. Does this number mean anything to you? Like, I can visualize 40 miles per hour, right? I can visualize 20 miles per hour, but I personally, I don't know about you guys, but I can't visualize 0.0639 kilometers per year. That number doesn't mean much of anything to me, all right? I can understand a year, right? A year is a pretty long amount of time, but 0.0639 kilometers, like what is that? So is this answer right? This is the correct answer, but I also like to understand my answers and like I want them to make sense to me. So I would like to make sense of this number with you if you'll keep listening to me. So what I want to do is I want to convert 0.639 kilometers per year into meters, right? And so I'm going to go from kilometers to meters here, and we multiply by 1,000. So I'm going to take my answer of 0.639, multiply it by 1,000. And when we do that, we get 63.8. That's meters now per year. All right? It's the same answer, right? This is kilometers per year. This is meters per year. I know how long a meter is. A meter is about 3 feet or so. An American football field. Now, the NFL, they play on fields that are 100 yards long. That's 300 feet. And so a yard is actually really close to a meter. It's close enough, essentially. You can look up over here. Actually, it says yards are 1.09. It's real close, all right? So this actually kind of makes more sense to me. The glacier moved about 2/3 roughly of a football field every year. So that's a lot of movement every year, but it's over the course of a year, so 365 days, right? So it's not moving a lot every day by any means. It's not moving very fast, but over the course of 72 years, that's a lot of movement. That's close to 5 kilometers total of movement. So yes, this answer is correct, but then I think this answer down here, the 63.8 meters per year, I think that makes more sense in my mind. Like I can visualize and understand that number better. Hopefully you guys can too, because I don't know what 0.639 kilometers is, but 2/3 of a football field. I watched the game the other day. That makes more sense to me. I can visualize that distance. Okay. For the last question then on the worksheet, question 6, a recent study of plate tectonics concluded that much of North America is moving westward at approximately 1.8 centimeters per year. At this rate of motion, how far will North America move in the next 25 million years? So they want our answer in both centimeters and kilometers, okay? So we have our equation, right? Rate is equal to distance divided by time, right? Now, for this one, they're actually kind of changing it up on us a little bit. They're giving us the rate. We know the rate, and we know the time. What we don't know is the distance. They want our answer in both centimeters and kilometers. They want the distance, right? And so we know the rate. We know the time. If you guys are comfortable with algebra, you can rearrange this equation. I'm not the best at math by any means, but what we can do is if we multiply by t on one side, we multiply by t on the other side, right? We get distance is equal to rate. This is multiplied now by time, okay? And so we're going to use this equation then for 6 to solve it. Furthermore, we can, kind of jumping back up here though, we can solve this also for time. If we divide by r, we can get time alone. So t is equal to distance divided by rate. I don't think we have any of these on this worksheet, but there might be some of these in the book. Or you might see them in the future, right? But make sure you're able to solve these rate equations as long as you have any of the two variables, right? You can solve for the third one, okay? And so distance this is what we're using for question 6 here. Distance is equal to rate times time. And so we know our time is 25 million years. We know our rate is 1.8. So we got 1.8. This is in centimeters per year. This is equal to our rate. And then we've got 25 million years, my for million years. And this is equal to our time. So we're going to plug this into our equation. So we're going to do 25 million years times 1.8, and it's in centimeters, all right? So what I'm going to punch into the calculator, it's going to be 25 for 25, and I got to put in millions here, so I got to put in all the zeros, okay? So I got to put in 6 zeros, 1, 2, 3, 4, 5, 6. Multiply that by 1.8. So 25 with 6 zeros to make it 25 million, all right? Multiplied by 1.8. I punch that into my calculator, and then I get 4, 5. And how many zeros? 1, 2, 3, 4, 5, 6. So 45 million. That's what I get. 1, 2, 3, 4, 5, 6. All right, put in my commas here. Again, not the best handwriting. I apologize. Our units, though, are going to be centimeter. What is it? The years, I think, will cancel. Yeah, the years cancel out. So this is just in centimeters, right? So 45 million centimeters is how far North America will move in the next 25 million years at that current rate of 1.8 centimeters per year, okay? I gave you guys the answer in centimeters here. I want you to figure it out in kilometers. Don't forget to include kilometers in your answer. And that's all you got to do for the first worksheet here, okay? Again, if you have any questions, please, please, please let me know.